So today we're going to be moving on to modular inequalities. And actually modular inequalities are quite a simple thing to understand. And there are a couple of little rules that we can learn in order to make it easier. But it's better to understand where these rules come from rather than just learning the rules themselves. So let's consider any modular function. Okay, we know perhaps that this is a linear modular function. And we can kind of generalize what the shape of this function is going to be. It's going to be something that will always have a positive solution, right? Based on the fact that it is a modular function. And when we're asking in this inequality here, what we're asking is, where is this modular function less than some constant? So Q is a constant. And if we understand modular functions, we understand actually that Q has to be greater than 0 in this case. So all Q is some line, right? And if we imagine this inequality, we can see the places where Q will be less than the line will be between the two intercepts. And so what we can do is we can generalize this and say, if we have some modular function and we are asking where it is less than some line, some constant, okay, the easiest way to solve this is to say we're looking for the values between the two intercepts. And this can be found by saying we want the values between minus Q and P, and between positive Q and P. And so we have a generalized rule in order to solve these much faster. Now in the same sense, we could ask, where is this modular function greater than the constant? And if we draw exactly the same example again, what we are asking ourselves is, where is the modular function greater than? And in this case, we can see this happens on the outer edges of the intercepts. And so once again, we can generalize this and say when we want to find out when a modular function is greater than a constant, right? Again, this constant has to be greater than 0, right? Either the constant or the modular function is going to be greater than Q, right? Because it's on this outer edge here. Alternatively, we want to know when this constant is less than negative Q, and that is when it occurs over here. So we've generalized two rules just by looking at these things visually. Okay. Now one or two other rules that we can use, which we've actually already looked at when we were looking at solving modular equations, right? So if we have some modular function and we want to find out when it is greater than or equal to another modular function, right? We can say this is equivalent, again, just like with the equations, where we say p squared must be greater than or equal to q squared. And in the same sense, we could also ask where this is less than q, and this is equivalent to saying where's p squared less than and sometimes equal to q squared. Okay, so these are the 4 rules that we can apply when we're dealing with modular equations to solve them faster. Okay, however, just by explaining this, you can see we can actually solve these graphically as well. So let's move on to a simple example here. Here we are asked to find out where this modular function is less than 3. We can use one of our rules. This is the less than rule, so we can imagine this is where we have a modular function that is going to be less than a line, and that happens between the two intercepts. So we can use this rule over here. So what we can say is we want to find out when we have minus q is less than, or p is, greater than minus q, but less than q. Okay, so the constant is q, and the modular function is p. And now we're just going to substitute, and we're actually going to solve a double inequality at the same time. So we're going to put p in the middle, and we're going to put positive q on the one side, and negative q on the other side. And from here, we're going to solve on both sides of the inequality. And just like an equation, when we do something to any one of these three parts, we have to apply it to the other parts. So in the center here, I have 2x minus 1. I want to add 1 in order to get rid of that. So I need to add 1 everywhere. So minus 3 plus 1 becomes minus 2. Minus 1 plus 1 becomes 2x. And 3 plus 1 becomes 4. And once again, I want to get rid of this 2 in front of the x, so I'm going to divide everything, all three parts, by 2. And I'll get minus 1, x, and 2. And so I've actually found the values for x where this inequality would exist. These are the x values where this modular function will be less than 3. Now we can also solve this graphically. And to solve this graphically, what we can do is we can consider this as y equal to the modular 2x minus 1 and y equal to 3. And we want to find out where the one is greater than the other. So we can graph the modular function by saying, well, when x is greater than or equal to a half, the equation remains 2x minus 1. But when x is less than a half, we want to consider minus 2x minus 1. And these are two very simple things to graph. So they have the vertex at a half and a gradient of 2. And so they would look something like this. This one is going to go through positive 1. So here we have our two separate parts of the modular equation, right? And we can label this one as y equal to 2x minus 1, and this is y equal to minus 2x plus 1. And we want to know when this modular function is less than 3. And so we can draw the y equal to 3 line in, and we can visually see this will happen when they intersect here and when they intersect over here. And while we can gather the results from our drawing, the best thing to do would be to solve these algebraically. And this point A intersection here, this is where the graph or the line minus in brackets 2x plus 1 is equal to 3. So we're looking for minus 2x plus 1 equal to 3, 2x plus 1 equal to minus 3, 2x equal to minus 2, x equal to minus 1. And we can see that visually as well. And on the other hand, we're looking for where 2x minus 1 is equal to 3, 2x is equal to 4, x is equal to 2. And this is visually where b occurs. So that's how we could solve these graphically. Now obviously we can see that solving this algebraically was much faster, and that's why we learned these little rules. Okay, let's move on to another example. Here we're asked to solve where this modular function is greater than a constant 4. And so what we can consider, if we go back to our original, is where if we have a modular function greater than the constant, this happens on the outer regions of the intersections. So once again, we need to find these points graphically. Alternatively, we could use the rule that we've learned. So the rule we're after is if we have some modular function p greater than some constant q, we can say p is going to be greater than q, or p is going to be less than minus q. So let's do the algebraic method first. Algebraically, we want to look where 2x plus 3 is greater than 4, or where 2x plus 3 is less than minus 4. And so we'll get 2x greater than 1 and x greater than a half. Or alternatively, we'll have 2x is less than minus 7 and x is less than minus 7 over 2. So there we have our two solutions. Once again, let's look at how we could solve this graphically. So we have the graphs of y equal to, well, we're going to have 2x plus 3. And this is when x is going to be greater than minus 3 over 2. Or we're going to have minus 2x plus 3. And this is when x is less than minus 3 over 2. So minus 3 over 2 is just minus 1.5. And we're going to have an intersect of positive 3. We need to draw is the y equal to 4 line. And so we have solutions over here and over here. Now we got solutions of a half, which we can visually see here. And we got a solution of minus 7 over 2, which is just minus 3.5, which we can see here. Now we could go and prove these by writing in the correct equations. This is the graph of y equal to minus 2x plus 3. And this is the graph of y equal to 2x plus 3, and we want to know when these values are equal to 3. So to finish off our graphical one, we could say we want to know when the graph is greater than the red line, and we could see that happens when x is less than this value, or in other words, when x is less than minus 7 over 2. And alternatively, this is also when it is greater than a half. A different kind of inequality. Here we have an inequality where we have one inequality greater than or equal to another inequality. And so we can use the rule, just like with the equations, where we look for p squared is greater than or equal to q squared. It just saves time instead of having to consider both the positive and negative cases. Once again, we have to remember that this rule only works when we have one modular function and another modular function on the other side of either the equal sign or the inequality. If there was, for instance, something attached on the outside, we wouldn't be able to apply this rule. So using this rule, we can say that we were looking for where 2x plus 1 squared is greater than or equal to 3 minus x squared. And this is just a simple quadratic inequality which we've dealt with before. So we need to expand the brackets on both sides. And we need to now move everything over and make one side equal to 0. So we'll get 3x squared on this side, plus 10x here, and minus 8 is greater than or equal to 0. We need to factorize. So fortunately 3 only has two factors, 3 and 1. And now we need to consider values for 8. That would give us 10. 2 and 4, so I think we can go 12 minus 2. Now we can't find solutions here because we're not being asked to solve an equation, we're being asked to solve an inequality. So we're being asked to solve where is this inequality greater than 0. And this is a quadratic, so what we're asking is what part of the quadratic is above the x-axis. So what we do is we find the critical values And those are basically the solution. So where x is equal to 2 over 3, or when x is equal to minus 4. And what we can do is we can plot these on a simple number line, minus 4 and 2 over 3. This is a positive shaped quadratic, right? And what we're asking is where it is greater than 0. And it's greater than 0 when it is over here and when it's over here. So this happens to be on either side of the two x-intercepts. And so our solution would be, we're looking for where x is less than or equal to minus 4 in this case, or when x is greater than or equal to 2 over 3. Once again, we could have considered this graphically, and what we were asking is where the modular function 2x plus 1 is greater than the modular function 3 minus x. And so once we've graphed that, we can visually see that this would occur over here and over here, right? And that was on the outer edges of our critical values.